In this video, we are going to look at how we can determine the volume and the density of an irregular object. Now let's begin by volume. Now before we look at the volume in terms of calculations, there are some basics that we need to know about volume. So number one, we will just look at the measurements for volume. Volume can be measured in cubic centimeters, can also be measured in cubic meters. Then we also have decimeter cubic. It can be measured in liters. It can also be measured in milliliters. So these are some of measurement or examples in which volume can be measured. Now the definition for volume is just the total amount of space. So whenever we look at volume, we are looking at the space occupied by an object. Then away from the space, also volume is a scalar quantity. It's a scalar quantity because volume tells us only the magnitude. There is no direction involved in volume. Now, away from knowing the units, then also the definition as being the total amount of space and also being the scalar quantity, we have to know the ways in which we can calculate the volume. So there are the method that you can use to calculate the volume of an object depends on the type of an object. Let's say if you have a regular object such as maybe like a cuboid. If you have a cuboid where the shape is regular like this one, you can use the mathematical formula. But if you are dealing with an irregular object such as a stone, okay, so such as a stone, we can see that here the shape is irregular since we cannot tell which one is length, breadth, or width. Now, for a regular object such as a cuboid, where we have our length, then we have our breadth, and also we have a edge, which is our height. We can use the mathematical formula where the volume for a cuboid is equal to base times the height. So base multiplied by the height. So from the cuboid here, so this is a cuboid, we can see that the base here is a rectangle. So the area of the rectangle is L times B, then multiplied by our height. So therefore, the volume for a cuboid is L times B times the height. So LBH. So this is the mathematical formula for a cuboid. Now, in a case where you have a cube, so a cube is a figure or a shape that consists of squares where the distances, all the distances are equal. So here we have length, also here length. So in a case where the three or the distances are equal, you are dealing with what we call a cuboid. So for a cube, a cube, all the distances are equal, and each distance is known as a length. And the formula for a cube is L times L times L, which is same as L raised to the power 3. Now, there are also some, you may have maybe a cylinder. So as long as if you are dealing with an object that is regular, you are going to use what we call the mathematical formula. Now let's move on. Let's look at if we are dealing with an irregular object such as a stone. So here we are going to, we need to have a measuring cylinder. So here we have a measuring cylinder. Okay, so let's say this has numbers like 10, 20, 30, 40, up to, let's say, we have 50. Then we can say it is measured in milliliters or in cubic centimeters. So here, the first step that we are supposed to do is we need to have water. So first we need to measure water. So let's say we measure water up to height of 20 milliliters. So here we have water. So the volume of water before the an irregular object is immersed is known as the initial volume. So this is what we call initial volume. So we have the initial volume here, and in some books you may find it as V1. So whenever you see the V1, this is the initial volume, and it is just the volume of water before the stone is immersed. So now here, let's say now we have an object such as a stone, and this time we have placed this object in water. So we are expecting the water to rise to a certain height. So here we can say we have an object inside here. Okay, so let's say we have 10, 20, 30, 40, 50 milliliters. So now we can, let's assume now after the stone was immersed in this water, the water rose from 20 cubic centimeter to 30 cubic centimeter. So this volume now, after we've placed the stone, this is what we call the final volume. So we have the final volume, which is denoted in some books as V2. Now, if we want to find now the volume of this stone, what you have to do is we need to subtract the initial volume from the final volume. So therefore, if we have an illustration like the one that we have done, for us to come up with the volume, we can just say volume of, we are dealing with a stone here. So volume of a stone, which is an irregular object, is equal to final volume minus the initial volume. So the final volume is V2 minus V1. So it depends with the book that you are using. Some books you may find it to be VF minus VI. So where the F is final, the I for initial, depends the book. So our final volume, we are going to look at this. So now the other thing that we can also know is 1 mil is equal to 1 cubic centimeters. So instead of using the mils, let's use now the cubic centimeter. So the final volume, we are looking at where the level of water is. So the level of water is at 30 cubic centimeters minus the initial. The initial is 20, and make sure that the initial must always be less than the final volume, because it was the volume before water was displaced by the stone. So 30 cubic centimeters minus 20, we are expecting to get the answer of 10 cubic centimeters. So this is the first method that we can use to find the volume of an irregular object. Let's also look at another way. This time we are going to use what we call an Eureka cane. So we have an illustration like this. So here we now have our measuring cylinder here, which is also numbered 10, 20, then we have 30, 40 up to 50 somewhere here. Okay, so now our first step that we need to make sure, we need to fill the Eureka can with water up to the spout. So we have to make sure that our level of water reaches the spout here. So after we are filled with the Eureka can with water up to the spout, we need to tie a thin string to a stone and gently lower it in water. So we need to now lower our stone here. So after we've lowered our stone in water, we are expecting the water to rise and also to flow through the spout here. So we are expecting water to, so you need to wait until the water stops moving from the Eureka can into the measuring cylinder. So here there is nothing like subtraction or what you just have to do is you need to look at the level of water, the point at which the water has reached after it is done falling into the measuring cylinder. So here we can see that the level of water is at 10 cubic centimeters. So we can say now the volume of the stone is equal to 10 mils, or we can just say 10 cubic centimeters. So these are the two methods that we can use if we want to measure the volume of an irregular object such as a stone. Now, away from the volume, let's look at now density. So density is the mass per unit volume of a material. So density tells us how close the particles are. So the formula for density is equal to mass divided by volume. So the symbol for density, the Greek letter symbol for density, something like a P, where we have mass over V here. Or maybe you can just use the letter D. Okay, now away from there, the units for density can be measured using, if we are using mass, therefore our volume should be in cubic centimeters. So grams per cubic centimeters or kilograms per cubic meters. So these are the units of density. Then away from the units and the formula, also the definition for density, we can now have, let's have the first example. Okay, so the example, the figure below shows a cuboid contained water. So contained water that has 5 square base and contains water to a height of 6 centimeters. Okay, so this should be the figure below shows a cuboid container that has a 5 centimeter square base and contains water to a height of 6 centimeters. Then the first question we have, what is the volume of water? So we can see that we have been given a cuboid. Then this cuboid has a base that is made up of a square. Then the depth or height of water is 6 centimeters. So the volume, the formula should be volume is equal to base area. So base area multiplied by our height. So you can see that the base area is a square. So a square is L times L. The area of a square is L times L times the height. So we can see that the base area, the length is 5 centimeters multiplied by another 5 centimeters times our height. The height here is 6 centimeters. So 5 times 5, that is 25. 25 times 6, that is 150. Then centimeter times centimeter times centimeter, that is centimeters cubed. So this was the volume of water, and remember, this volume is what we call the initial volume, since it is the volume indicating before the immersion of a stone. Now, for question 2, now a stone is immersed into the water in the cuboid, causing the water to rise to a height of 8 centimeters. So now we can see that after the stone was immersed in water, the water rose to a height of 8 centimeters. So from 6 centimeters, water went to a height of 8 centimeters. So the question is now calculate the volume of the stone. So if you want, we can make another illustration here. Now this time we have a cuboid that contains a stone. So the base did not change. So the base remained 5 centimeters multiplied by 5 centimeters. So we have 5 centimeters here, and also, so the only part that changed after the stone was immersed was the height. So the height of water rose to 8 centimeters. So we need to have the stone here. So now after we are done with this one, we can now find the new volume. So the formula is the same. The volume is equal to L times our H. The length, which is the base, did not change, so this remains 5 centimeters times 5 centimeters. Now our height, this time the height has changed from 6 centimeters to 80 centimeters. So volume is equal to 5 times 5 is 25. 25 times 8 is 200. So the final volume is 200 cubic centimeters. Now we need to find the difference between the two volumes. So therefore the volume of the stone is equal to final volume, volume 2 minus volume 1. So volume 2 is 200 cubic centimeters minus volume 1 is 150 cubic centimeters. 200 minus 150, we get 50 cubic centimeters. Then the other way, we can also find the volume of this stone. We can now say volume of the stone. This time, let's just look at the increase in terms of height. So the height that increased was 2 centimeters. So what we can do is we can find a difference between the initial height and the final height. So the final height is 8 centimeters minus the initial height is 6 centimeters. So the height that increased was 2 centimeters. So we can now say volume is equal to L times H. So we get 5 times 5 times the height that increased was 2 centimeters. So 5 times 5 is 25 times 2, we still get our 50 cubic centimeters. Now we can now find the density. So the density of the stone for the question 3, if the mass of the stone is 80 grams calculate the density of the stone. So we can now say density is equal to mass divided by volume. Now here the mass we have been given is 80 grams divided by the volume is 50. We are looking at the density of the stone. So 5 into 80 is 1.6 grams per cubic centimeter. So this is how you can answer questions that involves the density and the volume of an irregular object. So that's it for this video. Thanks for watching.